Today we study C26, equivalence of Euler-Lagrange equation to Newton's laws, especially the Newton's second law. You can download this PDF file from K-pop Digital Library. You can visit here kpop.org, kpope.org. This is our digital library. You can find a table of contents. Escape from Scientific Absurdity Series C, and scroll down to find the C26, the equivalence of Euler-Lagrange equation to Newton's law. The PDF file can be downloaded by clicking this button, and Korean version lecture is uploaded now, and I'm recording English version at the moment. And if you click this, it's not working. Strange. The network is very slow. Anyway, you can click this to watch the video for the Korean version. And if you click this, yes, the network is very, very slow. This is connected to our digital library. We just have visited here, kpop.org. And yes, it's really slow. If you click this, yes, network is not so. It's a free subscription to YouTube. Our YouTube site can be visited here. Okay, here. So K-pop collaboration and information is available there. Our education materials are original, and we have published educational papers here. All right. Actually, I'm particle physicist. I have published many other papers regarding QCD, quantum chromodynamics. It delays very much. Anyway, let's. Okay, you can find what I'm working on for QCD. That is the mechanics of quantum mechanics, relativistic quantum mechanics of quarks. Okay, so we studied C26, equivalence of Euler-Lagrange equation to Newton's law. Number one, what is Newton's equation of motion? This is Newton's second law, F equals ma. F, force, a net force applied to a particle of mass m, has a relationship with the acceleration. So x double dot is the acceleration, x single dot is the velocity. Newton's second law can be expressed in terms of linear momentum. We say this is a linear momentum, mass times velocity. This is called the linear momentum. The time derivative of linear momentum is mx double dot. As far as the mass is independent of time. In fact, its mass has the time dependence in relativity. So whether we restrict ourselves to non-relativistic business or not, this one is valid in Newtonian mechanics and relativistic mechanics too. Recall that linear momentum is mass times velocity. Okay. So we considered a little bit about math. consider a function of y and function of x. And it does not depend on x, and the function g is not dependent on y. We define function f of y subtracted by the g of x. And this is defined by a two-variable function called h. Compute the partial derivative of h with respect to x. Because y is independent of x and f of y does not have x dependence, so it vanishes. Therefore, x derivative of h, this guy goes away, and we have a single term, single contribution. Next, we consider this. H is a linear combination of f and g, and f is a function of y only, and g is a function of x only. Therefore, this guy vanishes. If I take the partial derivative of h with respect to y, only this term, this contribution survives, and this one vanishes. If I want to compute the total time derivative of this, then we make an additional total time derivative. And we know this is nothing but this. We can substitute this. Okay, so let's go ahead with the kinetic energy. The kinetic energy of a particle of mass m in non-relativistic classical mechanics, kinetic energy is 1/2 mv squared, where v is the velocity of the particle. The square of a Euclidean vector is, according to Pythagorean theorem, we have a sum of the squares of each component. Compute the partial derivative of the kinetic energy with respect to the coordinate, Cartesian coordinate. We can see there is no dependence on x1, x2, and x3. The only dependence is x1 dot, x2 dot, and x3 dot. So there is no explicit dependence on x, so we have all such kind of derivatives vanish. Next, we consider the derivative of the kinetic energy with respect to the velocity, the Cartesian components of velocities, x1 dot, x2 dot, and x3 dot. We can apply the train rule. So we have a factor of 1/2 mass, and we take the derivative of sum of squares with respect to x1 dot, for example. Because x2 dot and x2 dot are independent of x1 dot, we can kill them. And the only term surviving can be computed by applying train rule. If we apply the train rule, this is 2 times the velocity of the x component. And then we have to multiply the derivative of x1 dot with respect to x1 dot. And we know this is trivial. The vanishing component of these two can also be computed in this way, and is explicitly they are all zero, and this is a trivially 1. And in summary, I have introduced the partial derivatives of the velocity of ith and jth, the Cartesian components. So in short, they are expressed in terms of a Kronecker delta we are familiar with when we compute the scalar product of the two Cartesian unit basis vectors. They are 1 if the two vector indices are the same, and they are 0 when The two indices are different. As a result, we can compute the partial derivative of the kinetic energy with respect to the ith component of the Cartesian velocity that is nothing but the linear momentum, ith component of linear momentum. So in summary, we have reached the point. So express the linear momentum in terms of the kinetic energy. Yes, so I can write the linear momentum in a linear combination of three Cartesian unit basis vectors. And they are each component or mass times a Cartesian component of velocity. And as we have found, this linear momentum can always expressed as a partial derivative of the kinetic energy with respect to the velocity of the ith component of the velocity in the Cartesian coordinate system. As a result, all of these three different vector components can be obtained directly from a single scalar function that is called kinetic energy. What about the other part that is force? Potential energy is defined by negative of work done by a conservative force. If it is not a conservative force, there is no way to compute the potential energy. So let us restrict ourselves to the case of the force only if the force is conservative. Even though the detailed explanation looks very busy, however, what I'm talking about is a very simple formula we learned in high school. Any functions, integrable function integrated over a certain range with a variable upper limit. If you take the derivative, then this is returning to the original form of the integrand. So this is integration and then differentiation. It is nothing but the identity operation of this operation applied to the integrand. Because our potential energy is the negative of the integral of the force, we can reach the point we can read this force by taking the derivative. By the way, this was the only a single variable function, but what we are talking about is a function that is a field. The field means the function of position, and function of position means that we have three independent Cartesian coordinates. Therefore, such kind of derivative is called gradient. And the reason why we have negative sign on it is due to the fact that work kinetic energy theorem states that the conservation of energy is achieved by choosing the negative sign on the work done by the conservative force. So this negative sign attached to the gradient operator of the potential energy applied to a potential energy, we can reach the point that we can read the conservative force. So now we are almost ready to attack the problem, to resolve the problem, to find out the find equivalence of the Euler-Lagrange equation to Newton's second law. Okay, we have found the force applied. The conservative force applied to a particle can always be expressed as a negative gradient of the potential energy. And potential energy can always be obtained by negative the work done by the conservative force. Now we'd like to show that this is called the Euler-Lagrange equation for vector indices 1, 2, 3. I runs from 1 to 3. And we call this Lagrangian function that is a scalar, that is kinetic energy subtracted by the potential energy. Remember that the kinetic energy is a function of velocity only. Sure, it may have a coordinate dependence. So if we work on a rotation, so such as a polar coordinate system to describe the motion of a two-body motion of a sun and planet to solve the Kepler's problem, but we let us simplify as much as possible our problem because we are not ready to attack such a very complicated problem. So we, if we consider the case that kinetic energy depends only on the velocity, so it is independent of coordinate x1, x2, and x3. On the other hand, the potential energy depends only on coordinate. So perhaps I should have replaced with a bold face here. So let me correct this. Okay, I have corrected this one into bold face. Show that the Euler-Lagrange equation is equivalent to Newton's second law of motion. Let's see. Kinetic energy from the kinetic energy by taking the partial derivative with respect to each Cartesian coordinate of a velocity, we were able to find the linear momentum for I runs from 1, 2, and 3. In addition, the kinetic energy is independent of coordinate, so I can find that partial derivative of the kinetic energy with respect to the Cartesian coordinate is vanishing. On the other hand, if we consider a velocity independent conservative force, or for example, there is a velocity dependent force such as magnetic force. So we have a different way, but in general, we could solve this kind of problem, but it is out of the scope of this lecture. We are not working on the electromagnetic theory. It is rather complicated. So we just suppress the velocity dependence in the potential energy. Okay, in that case, velocity independent potential. So from the coordinate space, the gradient of a potential is negative of 4. So we have found it already. All right. Because of these two relations, we remember that Lagrangian is kinetic energy subtracted by the potential energy. The velocity-independent potential, if we combine this, Lagrangian's velocity derivative is nothing but, because this guy vanishes, nothing but the linear momentum. All right. And then Lagrangian's coordinate derivative, that's nothing but the gradient, ith component of the gradient of the Lagrangian, because kinetic energy does not have a coordinate dependence. This guy vanishes, and only this one survives. A negative gradient. Oh, what's that? Negative gradient is the force. All right, so force is the time derivative of linear momentum. That is F equals ma. Force is found to be Lagrangian's gradient. Linear momentum was found to be Lagrangian's partial derivative with respect to velocity. Therefore, we can write F equals ma as a time derivative of linear momentum equals the net force. Okay, time derivative of linear momentum. What's that? This one is the linear momentum. Time derivative of linear momentum is this. Therefore, time derivative of linear momentum is the Lagrange's velocity derivative, and after that we take the total time derivative. So that is copied in here. And then equals what? Force, force. This force. Okay, I copied this one. Why don't we move this left-hand side to the right-hand side? And we have reached this point. This is called the Euler-Lagrange equation. And this Euler-Lagrange equation is nothing but F equals ma. The big difference between the two theories is that even though they are equivalent, we have found, Lagrange, Euler, and Lagrange has found that there is a single scalar function instead of vector function force field. From a single scalar function, we can derive the vector equation. That's a very nice point, because a scalar function is much easier to deal with, and there is a vector index I that runs from 1 to 3. This theory does not reduce a very simple case for a single particle. However, a system of many particle system, this Lagrangian approach is extremely useful to solve the mechanical problem. And this method can also be applied to the relativistic case too. By the way, finally, because Euler created the calculus of variation, he thought, and finally, Hamilton has found that this equation is coming from the minimization of another function. Actually, it is called functional. That functional is called action S, and we have a time integral of this Lagrangian. And this one is minimized. To make this action minimized, we need to require this constraint, or equivalently, at which this Euler-Lagrange equation satisfies, nature selects the path of a mechanical system along a physical path that we observe. So, Hamilton's least action principle can be used in a very simple way to reproduce the Euler-Lagrange equation. And because we have found that they are equivalent to Newton's second law, we do not have to worry too much about how to construct the equation of motion in a complicated system. Just apply the least action principle, just like the Fermat's principle, to reproduce the Snell's law. Okay, that's it for today. Thank you.